one of the major tasks of Smith chart would be to find impedance, okay, at any point on the transmission line. So you need to find out the impedance at any point or any plane on the transmission line. What do we mean by this? So I have a transmission line with Z0, say, which is 50 ohms, connected to the load, okay, whose normalized load value is 2 plus J1, okay. I have just changed the value over here. So this is 2 plus J1 is the normalized impedance value. So you do not have to normalize ZL in this case. Now let us say what is the input impedance seen at this plane, which happens to be at a distance D1 from the load. What is the input impedance seen at this plane, which is at a distance of D2 from the load, and so on, okay. So the input impedance seen at all these places can be obtained by this Smith chart in a nice and easy manner, okay. So as before, we begin by drawing some representative circles on the Smith chart, okay. So I am going to draw some representative circles. I will also draw the unit circle, okay. So if they do not look like circles, as I said, please excuse this drawing. You should look at the Smith chart that is there in your hand, okay. Now this is my Smith chart, okay. So let us say this is one more circle which I have drawn just to complete my chart, okay. So how do I find the input impedance on the transmission line? Is there anything else that I need to know? Well, you do not really need to know anything else, right. So all you need to know is what distance you want to calculate the impedance. Now here is a crucial thing. As you move along the transmission line, what happens to magnitude of gamma d? That would remain constant. Therefore, you are actually moving on the constant gamma circle or the constant SWR circle, okay. So this is what you are moving. So first step would be to enter, okay, enter your Smith chart, S chart with ZL bar, okay. So since ZL bar in this particular case happens to be 2 plus J1, so in my mind this is, in my graph this is 2 and then this is 1. So this would be the point that I am looking at. This is my ZL bar, okay. Now with that ZL bar as one point and with the center as another point, draw a circle of this radius, okay. So this circle is the constant gamma L circle, okay. This is the constant gamma L circle, okay. So any movement that you are going to do would be on this particular circle, okay. Next what you do, from the center you simply extend this point and read what is the value shown on the wavelength towards generator circle, okay. So let us say this turns out to be some 0.22 lambda, okay. This is just an arbitrary number that I am taking, it does not really matter. You have to verify that this number is correct, okay. So you enter your Smith chart with 2 plus J1 and then find out that you are actually at that particular point. So if you extend and then find out the reading on the WTG scale, now all you have to do is express D1 in terms of lambda, that is, say, is it 0.1 lambda, is it 1.15 lambda, is it 3.75 lambda, and so on, okay. And remember, whenever your distance D1 goes beyond 0.5 lambda, that means you have actually taken one complete revolution, okay. Therefore 1.15 lambda should actually be 0.5 into 2 lambda plus whatever the component that is less than lambda. So it is kind of a modulo 0.5 lambda that you are doing, and this is the distance that you have to move, because if you move this distance you are actually back to the same point, okay. So you extend, find out what is 0.22 lambda. Now on this WTG scale, how much distance you have to move? You have to move 0.15 lambda. So on this scale you move 0.15 lambda. So let us say on the scale you drop at this point, okay. So this distance is 0.15 lambda, okay. So at what point you have ended? You ended at 0.22 plus 0.15, which is 0.37 lambda. So let us say this is my 0.37 lambda, okay, reading on the WTG scale. Now what you have to do? You have to now draw from this one, you have to draw a line until it reaches the center. Now once you have reached the center, you look on the constant gamma circle where you are intersecting, okay. this would give you the value of input impedance. What is the input impedance here? This is approximately, so this is slightly greater than 1, so let us say this is around 1.1, and then this would be somewhere around, say, on the x-axis this would be something like this. Okay, so I am just writing this as point P2, and I would invite you to write down what is point P2. So something around 1.1 minus something times, to unnormalize the input impedance at P2. So this is actually the input impedance at P2, needs to be multiplied, this is normalized, therefore this needs to be multiplied by Z0 to obtain the unnormalized input impedance. Okay, you find this out, I will leave this as an exercise to you. Okay, now let us look at a third example of finding SWR given ZL and Z0. Now one way to do this one is to actually use equations, which is what the way I would suggest. However, if you still want to use Smith chart, you have to first find out what is gamma L, right? Draw the constant gamma L circle and then see on the Smith chart. Okay, so you enter your Smith chart with the normalized ZL. Okay, so you have your Smith chart in this way. There is a unit circle here. Okay, so you enter your Smith chart with a given value of gamma L. Okay, let us say this is the value of gamma L that I am entering, and from the center you find out the radius and then draw a circle. Okay, so this circle corresponds to constant gamma L circle, and we have just told you in couple of minutes ago, or maybe slightly more than that, wherever this constant gamma circle cuts the x-axis, or sorry, cuts the horizontal axis, that would be the value of standing wave ratio, right? Because this would actually correspond to R max, which is normalized, which is actually equal to SWR. Incidentally, if you extend this line and then find out how much you had to move, so let us say this is around 0.2 lambda and this is 0.25 lambda, right? So the distance that you had to move to get from 0.2 lambda to 0.25 lambda such that you got to the SWR actually tells you the position of V max, because on this side, right, the voltage would be maximum. That is why you get R max bar over here, and if you continue moving you would reach a certain point, right, which would be on the left side of this axis. Okay, at this distance, right, so you start from this one and you move all the way up to this distance, that would correspond to the position of V min. So in fact what we have found out is not just SWR can be found, we can also find out position of V max and position of V min, okay, all from this particular exercise. So where, what is the position of the first maximum, and as you come over here this would be the maximum that you would reach first. So to get to V max, the first V max would be located at 0.25 minus 0.2 lambda, right, which is actually 0.05 lambda, and if lambda is given to be say 10 centimeters, then this would be 0.05 into 10, right, so and so centimeters for your location to the first maxima. And what would be this value? This position of V minimum will be 0.5, because this is actually 0.5, right, minus 0.2, which is 0.3 lambda. So this is your position of V min. Okay, and the distance and the difference between these two must obviously be equal to lambda by 4, and that is what it is, right. So lambda by 2 corresponds to one complete rotation, lambda by 4 corresponds to 1/2 rotation, and when you actually move 1/2 you are inverting all the impedances, something that we are going to talk about shortly. Okay. So what is the next application for Smith chart that we are interested in? We have seemed to found out almost all of these different quantities, but we have not talked about finding the admittance. Okay, what is finding admittance mean, right? So your Smith chart, we have striven hard to tell you that this is actually an impedance chart, but turns out that Smith chart can also be used as an admittance chart. Now how do you do that one? You recognize that the reflection coefficient gamma, right, at any point on the transmission line, let us say gamma of Z, is nothing but the normalized impedance seen at that point, so call this as Z of Z. I know this is slightly confusing, but please bear with me, minus 1 divided by, let us put a bar over there, so Z bar of Z plus 1, this is your reflection coefficient. Now what is the corresponding expression in terms of admittance coefficients? I know z bar z is nothing but 1 by y bar z minus 1 divided by 1 by y bar z plus 1. This can be written as 1 minus y bar z divided by 1 plus y bar z, which can also be written as minus y bar z minus 1 by y bar z plus 1, right. So what it means is that reflection coefficient changes its sign by 180 degrees if you go 180 degrees away, right. So you start with the impedance, you find out some gamma z. Now if you go 180 degrees onto the other side, which would be diametrically opposite, you actually express gamma of z in terms of y bar of z, which is the admittance. Now there is a one-to-one correspondence between z bar of z and gamma of z, and this equation seems to tell you that there is actually a one-to-one correspondence between gamma of z as well as y bar of z. Therefore you can use Smith chart both as impedance chart as well as admittance chart. Okay. So to find the admittance, all you have to do is start on any point on the Smith chart which is given by the load or whatever the impedance, okay, and from that point, right, so you first move on the constant gamma circle, okay, until you find yourself on the diametrically opposite point, okay. So this is the diametrically opposite point which corresponds to the normalized admittance. For example, if this is the normalized load impedance, then this would correspond to, right. So if this is ZL bar, then this diametrically opposite part would correspond to normalized admittance YL bar, okay. So this is how you find admittances at any point, by going 180 degrees or finding, diametrically opposite points, okay. Now we have already talked about finding the location of V maximum and V minimum. You can try this V max, V min positions, okay, with this particular ZL bar, which is 1 minus J1, okay. This is already normalized, okay. You don't really require the value of Z0. Someone has sat down and normalized already this one to you. Now find out where you are going to get your first position of maximum and minimum, okay. I will give you the answers. You try to find out whether these answers are correct. So D max is 0.412 lambda, okay, and if since lambda is given as 5 centimeter in this particular problem, so this would be 0.412 lambda, which would correspond to 2.06 centimeter from load, okay. So if this is your load ZL and this is your transmission line, this one, so this is at 2.06 centimeter, okay. It turns out for this particular case, because there is the capacitive reactance down here, the location of this point will be on the lower hemisphere of the Smith chart, and as you go clockwise towards the generator, the first position that you would hit is actually V minimum. So the first position should actually be V minimum, and this occurs at around 0.1 centimeter, okay. So this is how the standing waves might look on the transmission line. Okay, so the first thing that you would hit would be a minima at 0.81 centimeter, okay, and the next you would hit a maximum. The difference between these two must essentially correspond to lambda by 4, okay. Let us look at another example. This time it's kind of interesting to look at this example in which you are going to find out the input impedance, okay, given Z0 is equal to 50 ohms, okay, and ZL is equal to 100 ohms, okay. You might say that there is, what is so great about this? The thing is that I want to give you a taste of what you would be seeing if your lengths happen to be more than 0.5 lambda. So if you say at 3.15 lambda from load, find out what is Z in, you would actually start with the Smith chart. So enter the chart. This is your Smith chart. You enter the chart with the value of normalized load impedance. What is the normalized load impedance? 100 by 2. Normalized load impedance is 100 by 50, sorry, which would essentially be 2. So let's say this is on the axis 2. Then you draw with this as the radius one circle, which is your constant gamma circle, okay. So on this constant gamma circle, you now have to move. What is the distance you have to move? 3.15 lambda. What is the value, if you take this point and then extend it on the WTG scale, what would be the value that you would read? This would be 0.25 lambda, but clearly 3.15 lambda is nothing but 6 into 0.5 plus 0.15 lambda, right. So which means that you start from this point 6 times, you come back to the same point, and from there you move 0.15 lambda, right, because that is the value that is lesser than 0.5. So you start with 0.25 lambda, then you move 0.15 lambda for a total of 0.3 or rather 0.4 lambda. So 0.4 lambda happens somewhere over here. So on the WTG scale you move, okay, and once you have moved, you then enter Smith chart by drawing a line till it reaches the center and see where it actually intersects this particular point, and this would be the value of input impedance. Okay, I will give you the answer for this problem. So the input impedance is actually given by 0.68 minus j 0.48 as the normalized value. The unnormalized value will be 0.68 minus j 0.48 into 50 ohms, right, because this is your Z0, and the answer would turn out to be roughly 34 minus j 24 ohms. Okay, so this is the input impedance as seen from a distance of 3.15 lambda. Okay, so if lambda is given as 5 centimeters, you are looking at a distance of around 3.15 into 5, which is approximately 15 centimeters from the load. Okay, we now look at one of the other important examples of Smith chart calculation, and this example can be used to measure unknown load impedances. Okay, to measure unknown value of the load impedance ZL. The method that we will follow, okay, there are other methods, okay, but this is the classic method in which the unknown load was measured. What would happen is, you first have a transmission line terminated in an unknown load impedance. Okay, so before you put it into an unknown load impedance, what you do is you terminate this one with a short circuit. Okay, so you replace the load by a short circuit on the transmission line and then make measurements to find out what is the standing wave ratio. Now to find standing wave ratio, you would need minima and maxima measurements, right. So minima, where does it happen? The minima happens right on the short circuit or on the load itself, right. So minima happens, the first minima happens on the load itself, okay, when the load is short circuited. Please note that when you replace the actual load, unknown load, by a short circuit, the first minima happens to be on the load itself. Then after every lambda by 2, this minima repeats. Okay, we don't want to know that second maxima and so on. Any of the maxima would serve as a, any of the minima would serve as a reference. To find SWR, you have found out what is V minima, you also find out what is the V maxima, and then find out SWR as the ratio of V max to V min. Okay, so you keep this calculation ready with you. You also find out position of first minima, right, if load side is short circuited. Okay, so if the load side is short circuited, the position of the first minima would be at the load itself. Okay, if you are unable to identify at the load, you can go slightly away from the load, okay, or from this particular point, and then take this as a reference. It does not really matter which one you take as the reference. Okay, so if it is, sometimes it is difficult to identify, short circuit right on the load, so therefore sometimes people go to the next reference node, okay, which happens to be the next position of the next minima. Okay, so anything can be chosen as the reference, so you can choose one or the other, doesn't really matter. For this example, I am choosing this reference to be on the short circuited point itself. Okay, now what you do, you replace the load, the short circuit, with the actual unknown load that you are going to measure. Okay, what would happen if ZL is not equal to short circuit? Then there will be a shift in the minima. Okay, so now the minima would shift and produce its own standing wave pattern. Okay, what is the distance to which there has been a shift? Note down that point. Okay, note down shift in minima. You might ask, why should we note down shift in minima, why not note down shift in maxima? Technically the answer is that it is easier to measure with much better accuracy the minima points rather than the maxima points. Okay, Therefore, when you actually calculate SWR, there is some amount of uncertainty in this calculation, and because on the Smith chart a slight change in SWR can totally change the values, this method was not very accurate. Okay, more accurate methods use what is called as vector network analysis or analyzers to find out the unknown load impedances. Okay, so this method of finding unknown load impedance, which was called as slotted line measurement, okay, because this was standardized by using a slotted line, is not very accurate, but for an application of Smith chart this might actually look okay. Okay, so we will assume that SWR is known, but in practice SWR is slightly unknown, and that slight unknown will actually change the value of the load impedance. Anyway, with that practical thing in mind, note down the shift in the minima. So in fact, note down what is D1. If suppose you have taken the second one as the reference node, no problem, you note down this reference, right? So which would be D2, let us call, and this distance is what you are noting down from the reference, how much did the minima shift. Okay, now once you have done that one, all you have to do is you start from the short circuit point, okay, and then move towards the load, okay, move towards the load until you reach a distance of either d1 by lambda or d2 by lambda, depending on which one you have chosen, but in any case the reference has to be on the short circuit. Okay, what would it mean? It actually simply means this: you start from the minima, right, and then move towards the load until you reach short circuit. But because you don't know what this d1 corresponds to, you are basically doing this in the opposite direction. So you start from the position of the short circuit, and I know that if you move from this point towards the load, I would actually be able to find out where the minima, where the minima shift is located, right. So with that, you simply move towards the load for a distance of d1 by lambda, right. So you would have actually measured this d1 in terms of some centimeters or something, okay, and lambda is given in some centimeters, so you normalize it, find out what is this d1 by lambda, and then move on the WTL scale from the short circuit until you get to this point. Okay, so on the Smith chart the steps are simple. You first start with the Smith chart, okay, and then you write down a constant SWR circle. Okay, that is something that you can do. Okay, so write down the constant SWR circle by choosing the center, and SWR is this point. Okay, so on the constant SWR circle you need to move how much? You start from the short circuit, okay, on the WTL scale you start from the short circuit and then you move until you move the distance of d1 by lambda and land at this point on the WTL scale. Next what you do, you simply bring in this value to the center, and this would be the value of unknown load impedance, which is normalized. To unnormalize, you need to multiply ZL bar by Z naught to give you the value of ZL. Okay, so please carry out this analysis, okay, for the values which I will give you now. SWR is 2, Z0 is 100 ohms, okay, and the distance d1 which the minima has shifted is 1.15 lambda from the load. Okay, assume that the first position, the reference is taken at the load itself. Reference is load position itself. Okay, so this is load position itself. So you find the answers and let us see what you are going to get. Okay, now there is one last application that I would like to consider, and this is perhaps very important application of Smith chart, and in general this problem itself is quite complicated. This is called as impedance matching. Okay, so the first question that you might ask, why should I match the impedance? So there are a couple of reasons why one should match impedance. The first and foremost important reason is maximum power transfer, right. So you will get maximum power transferred to the load when you actually match the load impedance with the transmission line impedance, or actually if you would have matched. So let's say this is your generator impedance and let's say this is your generator voltage. Okay, this is connected through a transmission line to some load. Okay, if this is all that is there, then the input impedance seen will not be equal to Zg, or rather it should not be, it wouldn't be equal to Zg complex conjugate, right. So only when the load impedance happens to be equal to this complex conjugate of the generator impedance, then there will be maximum power transfer to the load, right. So because this won't happen for a general this one, what you have to do is you have to adjust the transmission line in such a way that you should get this ZG bar condition, ZG complex conjugate condition. Now in many cases you will not be able to adjust the transmission line, therefore you will have to come up with a different way to match the impedance of ZL via the transmission line of impedance Z0, characteristic impedance Z0, such that this condition is satisfied. Okay, this is for the maximum power transfer. The second thing is to basically minimize reflections on either ZG side or ZL side. This is called as load matching or the generator matching. Okay, again the primary reason would still be to transfer maximum power. Okay, in a general case of impedance matching there will be reflections, but these reflections are actually cancelling each other, therefore you would be able to do the impedance matching. Okay, so only when you want to avoid reflections, then you have to choose Z0 equal to ZL or Z0 equal to ZG, or you put a matching network such that this Z0 looks as ZL and this Z0 on this side matching network would look as ZG in order to minimize the reflections on the line. There are several techniques of impedance matching. There are lumped element techniques, or there is stub matching, which is quite popular in RF scenarios. Okay, we will be looking at stub matching in the next module. Okay, so in the next module we will be looking at stub matching. Thank you.